Hello friends, today we'll going to derive lens maker formula. To derive the lens maker formula, we have to study the refraction by lens. In this part, we have to study the refraction through the convex lens, and we have to study the image formation of object by the help of convex lens. Here we consider one convex lens L. Let mu1 be the refractive index of rarer medium and mu2 be the refractive index of the denser medium. The line which is passing through the center of the lens, it is known as a principal axis. Let P1 be the pole of surface LP1N and P2 be the pole for the second surface LP2N. Let C be the center of curvature and C1 and C2 be the center of curvature for the surfaces LP1N and LP2N respectively. O be the point at which we will keep the object. Consider the incident ray coming from the object and incident at the first surface LP1N. After refraction, it passing through the second surface, an image I1 is formed on the principal axis. Let's draw the normals N1 and N2 passing through the center of curvature C1 and C2 respectively. Let I be the angle of incidence, that is angle made by incident ray OA with a normal. Now for refraction at first surface LP1N, we will write the equation mu1 by CO, that is the object distance, and mu2 by Ci1 is equal to mu2 minus mu1 by C1, as if the image is formed in the denser medium. Now this image will act as an object for second surface, and when it incident on the second surface LP2N, will get image at I on the principal axis. Now for the second refracting surface LP2N, will write the equation mu2 by minus Ci1 plus mu1 by Ci is equal to minus mu1 minus mu2 by Cc2. In this case, as if we consider the object is in the denser medium and the image is formed in the rarer medium. By adding these two equations, we'll get the equation mu1 by Co plus mu1 by Ci is equal to mu2 minus mu1 into 1 by Cc1 plus 1 by Cc2. Let R1 and R2 be the radius of curvature for the surfaces LP1N and LP2N respectively. U be the object distance and V be the image distance. By substituting these values with sign convention, we'll get the equation by putting CO is equal to minus U and Ci is equal to V, Cc1 is equal to R1, Cc2 is equal to R2, we'll get the equation 1 by minus U plus 1 by V is equal to mu2 minus mu1 by mu1 into 1 by R1 minus 1 by R2. Since the relative refractive index, that is refractive index, ratio of refractive index of denser medium with rarer medium is denoted by mu, we'll get the equation 1 by minus U plus 1 by V is equal to mu2 by mu1 minus 1 into 1 by R1 minus 1 by R2. For M2 by M1, we'll substitute mu and we'll write down the equation as 1 by minus u plus 1 by v is equal to mu minus 1 into 1 by r1 minus 1 by r2. Now let us consider the cases when the object is kept at infinity, the image is formed at the principal focus. That is, the object distance is infinity. We'll put u is equal to minus infinity and v is equal to plus f. So, the above equation will become 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. This equation is called Lensmaker formula. While deriving this Lensmaker formula, we have to make the assumption that the lens is thin so that the distances measured from the poles of its surfaces can be taken as equal to the distances from the optical center of the lens. The aperture of the lens is small. The object consists only of a point lying on the principal axis of the lens. And the incident ray and refracted ray make small angles with the principal axis of the lens. Also, from the above equation, we will get 1 by minus u plus 1 by v is equal to 1 by f. Now let us see what is meant by principal focus, first and second principal focus, how it is formed. To find the image of an object by a lens, we can principal take any two rays emanating from a point on an object, trace their paths using the laws of refraction and find the point where the refracted ray meet or appears to meet. In practice, however, it is convenient to choose any two of the following rays. That is, a ray emanating from the object parallel to the principal axis of the lens after refraction passes through the second principal focus or appears to be diverge from the first principal focus. Now to study the first principal focus, the first principal focus is the point on the principal axis of the lens at which if an object is placed, the image would be formed at infinity. Let us consider convex lens. Let f1 be the principal focus and f1 be the small f1 be the focal length. In case of concave lens, we'll study the object is placed at infinity and the rays are appears to be converged at f1. This is the first principal focus. Second principal focus. Second principal focus is the point on the principal axis of the lens at which the image is formed when the object is kept at infinity. In case of convex lens, when the object is placed at infinity and the rays coming from that object which are parallel to the principal axis are known as paraxial rays. After refraction, these paraxial rays meet at point f2 which is known as second principal focus. Let f2 be the second focal length. In case of concave lens, when the object is placed at infinity, after refraction, the rays are appears to be converged at f2, which is known as second principal focus for the concave lens. Now we'll derive the thin lens formula or Gaussian form of lens equation for convex lens. We consider one convex lens where C is the center of this lens. The line which is passing through this point is known as principal axis. Let f1, f2 be the first and second principal focal point. Now we'll keep an object AB in between f1 and 2f1. That is, the distance of the object lie between f1 and 2f1. Let us consider the image formation when the ray AM, which is parallel to the principal axis, after refraction is passed through the second principal focus f2, and another ray AC, which is passing through the center of the lens. After refraction, it will pass undeviated and meet at A dash, and will get the image A dash B dash. And this image is inverted in nature. Let U be the distance of the object from the center of the lens, that is, it is the object distance. Let V be the image distance, F be the focal length, R be the radius of curvature of convex lens. Now to derive the thin lens formula, we will consider two triangles ABC and A''B''C, which are similar. So applying the similarity property, A''B' by AB is equal to CB' by CB. Now we consider two more triangles MCF2 and A''B''F2, which are similar. Therefore, we can write down A''B' by MC is equal to B''F2 by CF2, or we can write down A''B' by AB is equal to B''F2 by CF2. Therefore, from equation 1 and this equation we will get C''B' by CB is equal to B''F2 by CF2. We can write down B''F2 in the form of CB' and CF2 as B''F2 is equal to CB' minus CF2. Therefore, our equation will become CB' by CB is equal to CB' minus CF2 by CF2. According to new Cartesian sign convention, CB is equal to minus U, CB' is equal to plus V, and CF2 is equal to plus F. Therefore, above equation will become 1 by V minus 1 by U is equal to 1 by F. Now let us see what is mean by linear magnification. Linear magnification produced by a lens is defined as the ratio of the size of the image to the size of the object. That is, M is equal to I by O. From this figure, we can write down the equation for this magnification as A''B' by AB is equal to CB' by CB. Now, according to new sign convention, we'll write A''B' is equal to plus I, AB is equal to minus O, CB' is equal to plus V, and CB is equal to minus U. Therefore, above equation will become plus I by minus O is equal to plus V by U. That is, the linear magnification is equal to I by O is equal to V by U. Magnification in terms of V and F, we can write down as it is the ratio of F minus V to the F. Magnification in terms of U and F, we will write down the equation M is equal to F by F minus U. Now we will study what is meant by power of lens. Power of lens is its ability to bend a ray of light falling on it and is reciprocal of its focal length. When F is the meter, power is measured in terms of diopter. That is, power is given by reciprocal of its focal length. P is equal to 1 by F. Thank you.